Hello. So in this lecture, I wanted to give an explanation of how to create your own custom CMOS gates. So yeah, for example, so starting out, we can see we have this situation where we have A or not B, and it looks very similar to an OR gate. And so you could imagine that maybe we could just implement this using like a standard OR gate and a NOT gate. And we could do this and we could draw it out. But what we can find is actually there is a slightly more efficient way of implementing this circuit on the transistor level. So so I wanted to walk through that example. Just a second. Okay, so if you remember, so when dealing with CMOS gates, you will have a pull up network, and this is built with PMOS. And then you also have a pull down network. And this is built with NMOS. And so we will walk through kind of more slowly how to implement the pull-up network and the pull-down network separately. So first, let's start out with probably the pull-up network, because I think it's a little bit easier. So we can start out, we can notice that we have A or not B. So you could probably think, well, an OR gate sounds a lot like just two MOSFETs in parallel with one another, because now if one of the MOSFETs is activated, then on the output we will see a 1, and if the other one is activated, then we'll see a 1. If both of them are activated, then that's okay. And so now in this case, we can just put on the gate, we can just put whatever the input should be. So here we have A and B not, but remember that PMOS are actually activated. So let me write it down. So PMOS are activated when the gate actually equals 0. So what we want to do is we actually want to invert both of these inputs right here. So because we want this PMOS to become activated when A is 1. So therefore we want to add a NOT gate so that now when A is 1, instead a 0 is fed into the gate. And then similarly, this B right here, we want to invert that as well, because that will activate this PMOS, and and that will activate the PMOS specifically now when B is 0. Okay, great. So this is now the pull up network done. So it's basically just implementing the exact logic expression kind of as you would expect, but you just go and invert each of the gates. So that is how you do a pull up network. Now the pull down network is slightly more complicated. And the way that you implement a pull down network is, remember, so you actually have to keep track of the time when every single situation in which this circuit should produce a 0. So the best way to do this, in my opinion, is actually with a K-map. So let's draw out a K-map. And this will just be this will be a 2-input K-map, so really easy. But we'll just have A, B, and we'll have the inputs 0 and 1, 0 and 1. And so when A is 1, then in both these cases we will have 1. When B is 0, we'll have 1. So therefore there's only one single case right here where the pull down network should produce a give me just a second. So there's only one case where the pull down network will produce a 0. And that is the case when it looks like when A is 0 and at the same time B is 1. So this is our expression for our pull down network. And let me highlight this just so you know. So the green is representing the pull up network, and then red is representing the pull down network. And great, so now we can take this logic expression and then we can implement this. So then we have probably 2 NMOS in serial, because when both of them are activated, that creates a closed signal all the way to ground. And and then of course we just have the values plugged in for the gates here. So we have not A and then B, and we don't need to invert these because because NMOS are activated when G equals 1. So it's backwards from PMOS. So therefore, it looks like we are complete with designing this this circuit. So I can now take these, combine these together, and there we go. Cool. So this is now our custom gate that implements this logic expression. Okay. However, notice that there is a slight stipulation that this problem gives us, and that is that assume that B arrives before A. So maybe the value, like imagine the logic driving the B signal maybe propagates just a little bit faster than the logic driving the A signal. So therefore, we need to make sure that that we account for this. So B arrives before A. So so if that's the case, then we need to make sure that our order of any MOSFETs in serial should be correct. And it looks like actually this is fine, because if B arrives its value first, okay, so B arrives its value, maybe A is still waiting. Okay, if B is given its value, then this NMOS will correctly discharge. It will be connected properly, and then this PMOS will be activated, and then that will finish flowing through more quickly. And this is different from if we had done it backwards. So let me show you what would be a bad solution for a CMOS gate. So potentially, if instead we had maybe B and not A in this order, well then first B would be fed in its data, but then B would be charging up from whatever this kind of high impedance unknown value is. This value right here, this is all kind of for naught. It's charging up on it, but it's not really an important value. And so finally then when A receives its valid value, at that instantaneous moment, finally when A is given the correct value, that is when the voltage is actually pulled from ground, and that's when it needs to charge up everything all at once. So therefore, it is very important, especially when dealing with CMOS gates at such a small level, at micro level, you need to make sure that you are ordering your serial MOSFETs very carefully according to the order in which each of your gate inputs arrive. So cool. Okay, so hopefully that makes sense. This was not too bad of an example. Let me just quickly cross this out. I'll call this bad. Okay. Now I want to move on to a slightly more complicated example. So here we have A or not B, C, or C, D. And we are also given the order, and then so the question now is okay, so with this more complicated logic expression, now how do we implement this using a custom CMOS gate? So so of course, like I've already showed, it's a little bit easier to start with the pull up network, the PMOS network. So I'll worry about this K-map in a second, because the K-map is generally used for the pull down network, because maybe we can assume that this is already in the most it looks like this is the most optimized we can get. I don't think we can use a K-map to simplify the sum of products expression any more than this. So okay, in that case, then we can just start drawing out our PMOS circuit. So it looks like we have PMOS for A, and then of course we invert it because PMOS are activated when the gate is 0. And then after that, then we have another term where we have B and not C. And then finally a final term with not C and not D. Okay. So there we go. This is now our pull up network. But let's just double check that our order is correct for this. So, okay, so it says that C arrives first. So if C arrives first, that actually means that we should probably put C closest to our voltage source. So actually, yeah, it looks like we did not quite do this correctly. So let's reorder these. So it looks like B should probably be down there. C should be right there. Okay, great. And then it says, then put A, then B, then D. Okay, it looks like everything else is fine. Most important thing was just putting the C at the top here. Okay, great. So that is our pull-up network. Done. Now let us move to our pull-down network. So of course, now we need to go and invert this. So go and copy this. So this is, we now need to invert this signal to figure out exactly when our NMOS should drive a 0 on the pull down network. Okay, so let's go and fill out this. So okay, so we have an A term, so let's fill in the A term. A term looks like it is all this right here, and then we have not B, C, so not B and C. Okay, looks like we have that. And then finally we have C and D. So C and D, it looks like it will be this column right there. Okay, that is now all of our ones figured out. So now our zeros will be everything that is remaining. And so all of these zeros now need to be driven by our pull down network. So now we need to figure out the minimum sum of products that gives us all of these zeros. So it looks like we can create a pretty large box right there. This will give us a pretty small term. And then unfortunately this 0, it looks like the best that we can do is just kind of wrapping around like this. Looks like that'll be a pretty big term because it's a box of only size 2, but that's okay. It looks like that's the best we're gonna get. So now we can take this logic expression, and so looks like we have not A, I'm drawing this big box first. So we have not A, and then we have not C. Okay, and then we OR that with this smaller rectangle right here. This smaller rectangle looks like it will be not A and B and not D. Okay, cool. So now we have this logic expression for our pull down network. Let me add another page. Okay, so now in order to implement this, so we will have so this first term will be just 2 NMOS in series. This next term will be 3 NMOS in series. So we will have not A, not C, and then this other one is not A, B, and not D. Tie these together. There we go. And let's just double check that we are using this correct order. So I'll copy this down. Okay, so it says C first, so we need to put C closest to ground. That looks correct. Let me just quickly double check I did this correctly. I may have made a slight mistake. Nope. Okay, yeah, looks like we're all good. Okay, and then after that, then we need to put A closest. So it looks like now we should bring this D away, put A there, and we can put D up there. And okay, great. So this is now our pull down network completed. And so we can then copy this. And then in order to finish this gate, we just combine it with our pull up network that we already created. Okay, And then here's our logic expression. There we go. So that is now our gate finished. So there we go. Okay. Hopefully this is kind of cool, because like maybe you're not used to thinking about logic expressions on a transistor level. Like, yeah, here we can very clearly see, like, you know, this CD term right here is driven by this PMOS, but then it's when we simplified it in our pull down network, things got a little bit complicated because now we needed to invert everything. Yeah, so it's quite cool. Something that maybe some of you have noticed is it looks like we could probably maybe combine some of these transistors and make a slightly more reduced version of this circuit. We could probably kind of put some of these things in parallel and make like multi-level schematics. I think it's totally fine to just kind of leave it like this, but if you want, you're welcome to try to reduce these even further into a fewer number of transistors. And I will, if you want to post it on like Piazza or something, I will be happy to endorse your post. I just noticed I forgot the little circles there, so let me add these back. Okay. Great, cool. Okay. So yes, very cool. You can make your own custom CMOS gates. However, these are not actually very common. And like you may think like, oh, it seems like it's pretty like a pretty quick circuit. I mean, we're passing through, like, in theory, like we're minimizing to the minimal number of MOSFETs. Like usually, like we're used to thinking of minimizing to the total number of like logic gates. So like getting rid of AND gates, getting rid of OR gates. But in this case, we can actually get rid of like transistors. So we can get our area really, really small if we use this sort of strategy. But what you'll find as you put like these kind of gates, especially as they get larger and larger, what you find is actually that they will be very slow. And these are actually not very common because of how slow they can be. And so I actually provided on the next slide, I created an example. I prepared an example where if we look at this AND gate, this is an AND 8 gate, meaning it has 8 inputs here. And yes, we can see our pull up network on the top with 8 PMOS all in parallel. And we have 8 NMOS in series at the bottom. And then we have an inverter at the end. This just simplifies some of the logic. Otherwise, we would probably have a few more NOT gates and things. The circuit wasn't quite developed in using the same algorithm as shown here, but it's kind of close enough, at least for this example. And what you will see though is the time it takes to like kind of charge up each one of these NMOS that is in series is going to take like k plus 1 like time, or like there are k plus 1 transistors serially that we need to either charge up or discharge. And k meaning like, yeah, if we have like an AND k gate where k is the number of inputs to this AND gate. And it doesn't seem too bad, but like what we can find is that other strategies will give us better. So we call this O of k. O meaning like the end behavior of this function. So as k increases more and more, effectively this expression is just the function k. And so now if we compare this with a more traditional way of thinking about problems that we've done a little bit more in this class, where instead we have like a cascade sort of effect where we have like 8 inputs that are kind of just fed into this tree like structure and then are reduced down into a single value at the end. And we can imagine that every single AND gate here kind of follows maybe this structure instead. And what you'll see is there's on a single like AND gate level, now there are 3 transistors that it needs to charge up, right? There's 2 NMOS right there, but then there's also another NMOS here. So there's 3 NMOS in total that it needs to charge and discharge. And so if we now go through 3 levels, once again, we end up using 9 transistors in total. Like there's 9 transistors in our critical path along this delay. So it's the same delay as an AND gate and 8 gate. But as we increase K, what will happen is by like an astronomical amount, this design will significantly beat out this design. And yeah, the reason for that is because the number of transistors that we are charging up in our critical path will be this expression, which is 3 times log base 2 of K. And so if I go and plot this on Desmos now, so I have Desmos pulled up right here, so we can see. Let's call this first one. So I'll call this slow of K is equal to K plus 1. So K plus 1, yeah, is this AND 8 gate right here. And now if we look at the fast one, F of K is equal to, this is 3 log base 2 of K. Then yeah, so for a little bit, it actually looks like the fast one is a little bit slower. And then as soon as now it equals 8, then now they are the same. And then after that, immediately we can see that our faster way of cascading everything like this, by cascading all of the gates, now our circuit becomes much faster. Yeah, because it effectively now is like we've now turned it into a logarithmic like time to charge everything. And yeah, so kind of for this reason, generally CMOS, like custom CMOS gates, are not actually used all too much, just because the number of inputs that you start throwing on ends up slowing things down. And at that point, if you are like limiting yourself to maybe only like 2 input gates, then it maybe is just worth it to just use kind of the basic primitive gates that we're used to, like AND gates, OR gates, and NAND gates, and OR gates, because the tools are already optimized for that. Like if you're writing Verilog, the tools are already optimized to work around those primitive gates. So yeah, there's really just not a lot of great tooling that really supports a flow with custom CMOS gates. So you actually won't really see this in Verilog projects, but you might see this if you are making like a super high efficiency, high power, like I don't know, high speed, I don't know, small processor or something, where like you just really need like as much bang for your buck, and maybe you have a very limited area. So yeah, in this case, it may be beneficial to use custom CMOS gates. Either way, I think it's still very interesting, and it's a potential research opportunity. So if you want to like play around with it, you could try like implementing your own algorithms to figure out like, you could try like converting like a Verilog netlist into using custom gates. I don't think anyone has done that in recent years. Could be kind of cool. So anyways, yeah, so just wanted to show you this lecture. Hopefully you learned something about this. And then yes, there will be a question on your homework and a question on your final about custom CMOS gates, because it is still important to understand. So okay, hope this was helpful.